expansion. Now, coming back to the problem we have at hand, if, what is the displacement in this beam at point B? In this given beam, what is the displacement at B? I want to remind you that there is a roller support at B, which is called a support because it is doing something. You know why we call it a support? Because it is capable of preventing something. Can you tell me why? What is that something? What is it preventing? It is preventing that vertical displacement at B, okay, and that's why you call it a support, okay. So if it is a very rigid support, sometimes we call it unyielding support. Unyielding means that it is 100% rigid, it doesn't deform, it doesn't settle down. So it's going to be like, I'm not going to let this end of the beam go up or down. It's going to be at the same level, okay. It's unyielding, it's not going to settle, it's not going to deform as well, okay. So that end will remain at the same level when the loads are applied, okay. So what is the displacement at B in this beam? What is the displacement at B in this beam? 0. Why should you be doubtful about that? It is 0. You call it a support. The reason for that is it is capable of preventing that displacement. Otherwise, why would you call it a support? Okay. So you know, the displacement of the given beam at B is 0. This is something we know because of the boundary conditions that we have at B. Okay. So we know that the actual beam, so I could write it down like this: delta B actual is equal to 0. In this particular case, I have assumed it is 0. If it is not 0, it's something else. If there is any settlement, you would be kind of given that value for the settlement. So you would know this delta B actual in all cases. Whether it is 0, so you got to just use the value of 0. If it is not 0, you will be given the value. So in all cases, it's something that you will be like you would know that value. Okay. Now, delta B actual is 0, but just for the sake of getting this redundant, we're gonna pretend that we don't know that value of delta B actual. Okay, just for the moment, we pretend that we don't know its value, and what we do is we find this displacement in the beam using principle of superposition. And what is that principle? You go like that, equal to just like this. So we will break this down into two parts. I would say, so what is the effect of, so when the support exists over here, what is the effect of that support? A reaction at B, because it is preventing the displacement at B, so it is going to have a vertical reaction at B, RB, okay? Now, if I temporarily remove that in this beam, and I say, I'm going to consider it separately. This is RB. Is there any problem with this breakdown? It's fine. We're just using principle of superposition. Nothing wrong. Okay? This structure which is obtained after at least temporarily removing the redundant, the remaining structure is called primary structure. So, of course, it has to be something determinate. Otherwise, I mean, there's no point in doing this practice, okay? So the problem was there was a redundant force, so you temporarily remove it in this structure, and then you consider it separately, okay? Now, this structure, in fact, without the loading is, I mean, something applied on the structure, but the structure itself does not include loading. The structure is, I mean, this support and this beam. So this is the primary structure, okay? Primary structure, so there are basically two conditions for a primary structure. One is determinate. Of course, it has to be determined. Second is it needs to be a stable structure. I mean, you cannot say, I'm going to remove this support and I'm going to remove maybe one more moment or something. So if you remove two redundants, what's going to happen? If you remove, for example, the momentability of this, if you get rid of that as well, you'll be left with something like this. It's not a stable structure. So this is not acceptable as a primary structure, because anything applied to it will make it rotate as a whole. So there's no analysis you can do. Okay. So there are two conditions for a primary structure. It has to be determinate, of course, but the more importantly, it needs to be stable. How do you make it determinate? You remove enough number of redundants so that the remaining structure has only only as many number of unknowns as you have the number of available equilibrium equations. So you remove enough redundants, but you make sure that you do not remove too many redundants so that it becomes unstable. So you got to make sure it is determinate as well as stable. So it's going to be a simpler structure, okay, stable and determinate. All right. So we were pretending that the displacement at B is not known, although it is, but we just try to find it by a superposition method, and then what we do is we treat with this external loading in the first step. So whatever external loading is applied, if the given beam consisted of, for example, another point load over here, another point load over here, we would have considered all those loads in this first part. So this is primary structure subjected to the actual, or maybe external loading, or maybe sometimes you can call it the actual loading. Okay. Now, can you determine displacement at B in this beam? It's a determinate structure, cantilever. There are so many ways to find, maybe conjugate beam method, maybe double integration method, maybe whatever area moment, whatever method you know, you can apply it. In this class, there is no restriction. You can use any method. You can even use a direct formula if you have the formula. I hope you have the formula for most of the cases. I remember we derived these formulas in our previous course, elementary structural analysis, where we derived these formulas. So that's the reason we derived them. Okay. So you can use ready-made formula. For example, in this case, it is W. I got to see this formula again. It is W. So this is delta B. There's a special name for this displacement. We call it delta B naught. This naught is for the external loading. So this is delta B, or should I say displacement at B due to the applied loading. Okay. So delta B naught equal to, the magnitude is W L raised to the power 4 over 8 EI, and the direction is downward. Of course, it is going to be downwards. For most of the cases, you will be able to predict the direction by just looking at the structure. Okay. So you can use, so in this course, in the exam, you are allowed to bring these tables where you can see the ready-made formula for calculating the displacements. Okay. And the displacement over here, we do it in a further simpler way. What we do is, RB is an unknown. So even if you try to apply this, if you try to define the displacement at B, it has to be in terms of this unknown RB. So what we do is, we apply a unit load at B. I need a high tension at this point. This is a real loading. There's nothing virtual over here. This is a real loading. What we do is we consider a unit load at B in the same direction as RB, okay, and then we find the displacement. So you may say, why don't we consider the full RB? I'm coming to answer your question, okay, in just a few moments. So unit value of reaction at B, so this RB equal to 1, and you find the displacement at B. Okay, this point is B. So it is again displacement at B. So the first subscript is going to be where the displacement is being found out. So it is at B. So you would say delta B. The next displacement will tell the location of the load. Okay. So this is called delta BB. Why we call it delta BB? You could use any symbol, but just to make it more systematic, make it easy to understand, we're going to stick to certain way of giving it a name. So it's small delta because it is due to unit load. capital delta, given loading, and there's a not as well, comma and not. And then small delta for displacement due to a unit load, and then these two are going to tell you point of displacement, and the second subscript will be for point of the force, where the force is being applied. So this is basically displacement at B due to unit load at B. Okay. So what is the, so far in our in your table you will find something like this. When there is a P at the tip of the cantilever, the displacement in that case is given by P, in that case it is given by PL cube over 3EI, okay? And of course it's going to be downward. If the load is downward, the displacement will be downward, okay? Now if I have a unit load, so the P value will be 1, okay? If I have a unit load, the P value will be 1. And if the load is upward, the displacement should also be upward. Agree? So instead of using any detailed method, we just resort to using a ready-made formula. Okay? So delta BB would be 1 times L cube over 3EI. Okay, and what is the direction? Upward, because this force is upward. So this is, delta BB. Now, if I want to use superposition, I have to work like that. So I would say this is delta B in the primary structure. Okay, the primary structure is something like this. Okay, this is the primary structure. Over here, the primary structure is subjected to the actual applied loading, the external loading, and then over here, the primary structure is subjected to a unit value of RB. Okay, so delta B in the primary structure would be equal to displacement over here in the beam, and this beam at B, and displacement at B in this beam. Okay, so it is equal to delta B naught plus. So this is just a vector. We are yet to put the value, the magnitude and displacement. We are yet to account for that. Okay, so delta B naught plus delta BB. But do you think this is fine if I write it like that? Is that acceptable? What's wrong with this? I'm not considering the actual value of RB. I'm considering a unit value of RB. So this delta BB is due to a unit value of RB. If in actual, for example, RB happens to be something like 15 kilonewton, let's say. So what should be the displacement due to that 15 kilonewton of RB? Whatever is the value for unit load, you multiply that by 15. It looks simple. You put 1 over here because RB is considered 1 in this location. It's not actually 1, but you do it in this way. You do it for 1 unit value of RB, and then you add up and you multiply RB later on. Getting it? Simple enough? If I wanted to do it for RB, I would go like this. Isn't it ultimately the same thing? If I call this term as delta BB, it's ultimately the same thing. So this is not how we do it. We prefer to do it in 2 steps. We consider a unit value of RB, okay, unit value of RB, and then we later multiply that value by RB. So the displacement is multiplied by RB. So you get the displacement due to the full value of RB. Okay. Now this is the delta B in the primary structure using the principle of superposition. Okay. Now you have been, so let's say this displacement in the primary structure at B, which we have found using the principle of superposition, should be the same as the delta B in the given structure, in the actual structure. So delta B actual should be the same as delta B primary, Okay? And that we have found to be equal to this, delta B naught plus delta BB times RB. Now, if delta actual in this beam is known to be 0, for example, because there is unyielding support or whatever is the displacement that is given to you, so this term would be something known to you. Okay? So I could write it down like this. RB would be delta B actual minus, so you can look at the equation like this, okay, minus delta B naught. So just imagine if this term is 0, it will disappear, but I'm purposely not putting the value of 0 to make it a generalized equation. Okay? All right? Divided by what? Delta BB. Now, delta B naught is known, delta BB is known.